Hello, everybody. We are about to start the next presentation. Patrick Lucy will be talking to us about the thin edge of the wedge, accurately predicting shot outcomes in tennis using style and context. I'd like to welcome Patrick to the stage.
Great. Well, thanks for showing up. Obviously, tennis isn't as popular as basketball, but that's okay. That's okay. So today I'm just going to talk about some of the work we've been doing in predicting player behaviour in tennis using tracking data. So the majority of this work was done by a very talented PhD student, Felix. He's back in Australia finishing his PhD before joining me at Stats as part of the new data science group which I'm forming. Also, Stuart Morgan from the RAS has been a great contributor. Also, Makar Reid at Tennis Australia, who we've been able to get this data from. So let's get started. So most of you are aware, if you follow tennis, we've had this great data source for the past 10 years in the form of HawkEye data. So in terms of visualizations and broadcasts, it's been really powerful. Also in terms of umpiring, helps aid umpiring decisions. On the other hand, we have the SLAM tracker from IBM. So really, really cool predictive analytics there. They use event-based data. Prime example of this is showing the keys to the game. So here we have the final between Djokovic and Murray, and they just show the top 3 things that each player should do to beat the opponent. But it's rather curious. So even though we've had all this data for a long period of time, the tracking data hasn't been actually used to drive the predictive analytics. So most people in this field know actually getting access to data is the big bottleneck. And also with the HawkEye data, it's not in every tennis court. So that is the bottleneck. But through our collaboration, we've been able to analyze the data and do some cool stuff. So basically what we wanted to do is see who's dominating a point. We have this fine-grained data. We actually want to see if we can get an idea of who's actually dominating the point or not. So here, I just show an example between Nadal and Federer. So if anyone's read Nadal's book, he says, if I have to beat Federer, the way I beat Federer is that my forehand is much better than his backhand, so I'm just going to keep hitting it to his backhand. And you see in this example that he does, he dominates the point until he just finishes him off. And so here in another example, have Nadal versus Nishikori. So Nishikori serves. There's a couple of shots in the rally. There's a change in momentum here, and then Nadal wins the point. And so this is what we call the thin edge of the wedge. So when a player wins a point with through a winner, that's not really informative. It's very observable, but we want to see what happens before that. So this is why we call it the thin edge of the wedge. Okay, so how we actually do it. So just in terms of prediction, we just have this simple pipeline. So you have HawkEye data, you can craft some features, and then we do a prediction to get a probability. Because so the data that we have is the HawkEye data. It comes in the form of trajectories. So we have the trajectories, the impact points of all the shots, also the player motion at a very fine-grained level. And so the features that we can craft are very simple. So the raw features could be the shot start location, the impact location, the average speed, the player movements, the angles, fatigue factor, all these different things that we can calculate directly from the trajectory data. And so here I have a nice visualization of some of these features. So we've just plotted the probability distributions of Djokovic, Nadal, and Federer when they hit winners. So in that first column, we have the impact location. So this is where they tend to hit winners against all players. So you can see down the bottom there, so Federer, he tends to hit the winners wider of the court. So this makes sense. He's got a single hand, forehand and backhand, so he tends to be able to go wider of the court. Also, if we look at the other side of the slide, we can see Federer tends to be inside the baseline when he hits a winner. So he's a serve volleyer, he volleys or his grand strokes are well inside the baseline. We can see with Nadal and Djokovic, they tend to be further behind the baseline, which again makes sense. So talking to Makar and Stu, who are the domain experts here, we also crafted some other features. So we call this dominance features. So we have ball speed ratio, which is just the change in velocity between the incoming and outcoming shot. The shot angle ratio between the shot maker and the opponent's positions between strokes. The depth ratio, So if I hit a shallow shot and I hit it very deep, that's very predictive of winning the point. Also the lateral movement ratio. And so this behavior tends to be very nonlinear. And so a nice way to model this is through a decision tree. But with a classification tree, we're only going to get a 0, 1 as an output. But a way to get around this, we just use a random decision forest, and then we just get a probability that way. And so to learn the hyperparameters of the tree and the forest, we can just test in a held out set, and then we can check where these two curves meet. Okay, so when we trained the classifier, our task for this paper was that we wanted to predict the probability that a player will win the point at any moment. Okay, so essentially this is win probability. We only focused on the rally here, so we didn't take into consideration the serve, and have some interesting stuff to talk about with regard to that later. So the data set that we had was 3 tournaments worth of data from the Australian Open. So the 2012 to 2014. In total, we had over 10,000 points. Within that, around 40,000 shots. And then the labeling for this data set was if the player lost the point, we labeled all those shots as 0. If the player won the point, we labeled all those shots as 1. And then we partitioned the data equally with the training evaluation set and test set. We also modeled the top 10 players because we're really interested in about personalization. And so we just looked at the top 10 players because they had the most data. Okay, so the way that we measured the performance is this through the RMSE. Okay, now I know Carl's done some pretty interesting work on this. So with the data that we had, we just wanted to see the impact of the server. So as most people know, the server will most likely win the point. Okay, so if the server gets the first serve in, it's around 68% of the time they win the point. When the server gets his second serve in, it's around 55%, which around the average is 63%. But what's really interesting, if we remove the aces or the forced error from the serve, the returnee is actually more likely to win the point. Okay? So if the server gets his first serve in, it's around about 47% of the time that they'll win, and then the second serve is around about 45%. And so it's not actually 50-50, so the returnee actually has the advantage when they get the serve back. So our baseline is around about 0.53 RMSE. And so these results just show you that we're actually getting some signal from the tracking data and we can improve performance. But a massive problem is that it's not specific. And so what do I mean by that? So we'll show this example again. So Federer against Nadal, Federer has his own distinct style. Okay? So it makes sense that we just model his behavior. But his behavior is dependent on the opponent. So as I said before, Nadal just tends to hit to his backhand. So his behavior is going to be different. So to do better prediction, we should be able to model this. Okay? So how do we actually do that? And so this causes problems when we actually model it. We have the raw features, but just say we have an indicator variable for each of the players, we're going to need a lot more data. And then we have the opponent, we're going to need even more data. Problem is that we're never going to have enough data to model every specific instance, okay? And what happens if they haven't played each other? And so this introduces the idea of player style. We all talk about player style, okay? But what does it mean? And why is it useful? So my favourite player is Federer. So we'll use him again. So just say, so I mentioned before, he's a serve volleyer, but how would we rate his individual attributes? So we could say, well, his forehand's really, really good. He's got a good backhand, but it's probably not as good as the other guys on the tour. His volleying's outstanding. You know, he's a bit of an artist. And also his approach shots, his overhead smash is really, really good. But just say he's playing Nishikori, okay? So they've actually played 6 times before, but just for this example, let's just say they haven't played before. How would he go about planning to play against this player? So one thing that he could do, he could just watch the tape, and then he could just rate the various attributes of Nishikori. But another thing that he could do, he could actually talk to other players, or he could watch the tape, and he could say, well, he's very, very similar to Andy Murray. I've got a lot of examples. I've played Andy Murray a lot. I know how to beat him. So how about I just employ those same tactics? And that's basically the idea behind learning a style vector. So when we're training a classifier for a very specific classifier, instead of saying, well, I have no examples, I can say, well, I've got a lot of examples against Federer and Murray, and Nishikori is very similar to Murray, so let's use those examples and build a classifier. And that actually allows us to do much better prediction and much more specific prediction. And so what that means in terms of our tree is that we have a nice compact style vector, and that allows us to train a model more adequately. Okay, so there's various ways that you could actually specify style. You could get an expert, they could draw, they could go through and they could rank all the attributes, or we could do this directly from data. And this is what we did. So we did it in an unsupervised way by clustering trajectories. And so what we had is, so just say we had two trajectories, the way that we parameterized it is just by equally sampling at the same time rate, and then we matched their, so we just compared their absolute XYZ location. So this way we incorporated the speed, the location, the spin. And then from that we looked at doing clustering. So the first clustering method that we used is just k-means, which looked to minimize the reconstruction error. But a problem with k-means is that it doesn't really, it's not very discriminative. And what I mean by that is that you can see each of those clusters, they're equal size, which makes sense. But we know in tennis that it's more important to hit the corners, the lines or in the corners. So we needed some type of objective function to capture that. And the way that we did that is using KSVD. Okay, so it's a dictionary learning method which basically minimizes the reconstruction error, but we put another constraint there where we can also minimize the prediction error. And that tended to give us pretty good performance. So we can tune this alpha parameter. So we found about 11 or 12 work best, and that gave us the best prediction error. Okay, so for the original dictionary that we learnt, we just used individual trajectories. But also, as most people know in tennis, that it has to incorporate the combination of shots as well. So we did this in a hierarchical way. So what we did is that we looked at the change in probability, and then we recruited those combos of shots, and then we clustered them in a secondary clustering stage. And so all up, we found a dictionary of 50 shots. And so what's really nice about having a dictionary, so now we can assign one of these labels to each shot. And now we can start to describe the player behavior. So we can just get a normalized frequency count, or just a frequency count of all the shots, and then we can compare histograms. And this is really interesting, right? Because we can see in terms of style, Federer is pretty close to Djokovic, as well as Berdych and Tomic. On the other hand, you have Murray, he's pretty close to David Ferrer, Nishikori, and Tsonga. And then Nadal tends to be off by himself, but he's left-handed and he has a very distinctive style. But the key takeaway point here is that we're doing it based on trajectories. So the speed, the location, all that information, and we're not handcrafting this. So we're doing better prediction, which allows us to do these similarity measures. And so using this information, again, we do better prediction. Okay. And so let's go back to the example here between Nadal and Nishikori. So we can do our prediction throughout the match, but using a style vector, because we can model this specific instance a bit better, we can actually do a lot better in terms of prediction. So on the bottom there, we show the video when we incorporate the style vector, and then we can superimpose one on top of the other. And so initially, we had that thin edge of the wedge, but actually that didn't really exist because Nadal had the advantage anyway. Okay? So doing better prediction allows us to do better fine-grained analysis, and that's just an example of that. But also context plays a very important role. For instance, who's serving, but also the game state. Whether it's a break point or whether you're winning or losing, all these different contextual information is important in doing the prediction. So we can include that as a feature as well, and we can do better prediction. Okay? And so we just have an example here on how that changes our prediction throughout the point as well. So we can see, but I'll play the bottom one. So when we have context, it actually changes the initial conditions, right? Our initial predictions. So in this situation, even though Nadal is receiving, he's far more likely to win the point because it's break point up. So these will change for every point. And so now we can start to quantify this behavior, which is really exciting. And so I get really excited about this because I think this is a really nice planning tool that we could use. So another example is, just say we're analysing the serving behaviour of players. Okay, so here we have a plot of what Nadal will tend to do against all players on all points. Okay, he tends to go down the middle a lot. But on break points, his behaviour tends to be the opposite. Okay, so on all points he tends to serve out wide 17% of the time, but on break points he tends to go 46% of the time. Now if you ask these players, they probably know that, but it's nice to be able to put a specific measurement on these types of things. And then also, you know, we, in addition to doing recommendations, we can actually do specific analysis. So we can do simulations. So just say I have an incoming trajectory. Wouldn't it be nice if we can put the probability distribution of where we think the next shot is going based on the identity or the context of the match? And this is what we can do now. So here we have plots of, given the same trajectory in, how Djokovic, Nadal, and Federer will change in their behaviour. Okay? So we have another trajectory, and then we can see how this changes as well. And in terms of doing this fine-grained analysis, we can come up with new metrics. You know, I think predictability is a really, really nice metric. So how likely is a player to be predictable in a certain situation? So in this plot, we can see that Federer is the least predictable of all these players, which makes sense. You know, he's got the most tools in his bag, but I think this is pretty cool. So now, so you can think about it in terms of entropy or predictability. So there's other things that we can do. And basically what motivated a lot of this work was, so I was at Disney Research beforehand, and we're interested in doing actually shot prediction, where we think the next shot is going before the shot's actually played. So just say you're watching ESPN or the Australian Open back home, wouldn't it be cool to light up on the broadcast where we think the next shot is going before it actually happens? And so again, example-based analytics. So given a shot, you know, we can start to put these values, these very specific values on the court, and we come up with these really nice visualizations. So this one was done by Tennis Australia, and I think, again, in terms of storytelling, I think this is really, really powerful. But not only can we do this for tennis, we can do it with any sport with tracking data, okay? So at the start of the week, we presented this idea on chalkboarding. So imagine if you had the ability to draw a play or find a play and find all the plays like that. And so we can actually do this. So you could do it in terms of situation, or you could draw a play in basketball, just a couple of players or all the play, put semantics on that, click retrieve and find everything like that. So basically, think about in terms of doing search for sport. Search for sport currently sucks, okay? Using this example-based analysis, we can actually solve search for sport. But we're just scratching the surface on what we can do. Imagine having the ability to have a play and actually doing analytics on that specific play. So the example that I have here is that I want to find the expected point value of this player scoring in this situation. What happens if I moved him around? What happens if I moved around the defender? Or what happens if I switch that player in terms of a lineup? Just say, I want to do, this player I think could do a better job in that situation. So doing very, very fine-grained analysis and analytics, I think is very, very exciting, and these are the types of things that we're doing at Stats. So that basically sums it up. So just the takeaway points, that using tracking data, we can do very fine-grained analysis, but we need to be smart with the data. Using these features such as style and contextual features allows us to do better prediction. So that's basically it. So I'll be happy to take questions now. Thank you.
Thank you very much. That was brilliant. We tend to think about where players are strong. How did you find looking at where players are weak in terms of prediction? And
So that's a very good question. So I'm not a tennis expert. I'm more of a tennis fan. But what we're more interested in is developing these assistive tools for domain experts actually to find these things. So it's very, very specific, right? So if we gave this to Macca and they play around with it, Tennis Australia, to say they're analysing what Nick Kyrgios will do on the court, not off the court, they could actually draw up these plays and do that very specific analysis. So in terms of finding these general metrics, that's basically not what we want to do, because we want to allow the domain expert to actually dig down to a specific example and find these patterns themselves.
So in terms of calculating player style, you had those distributions. Do you calculate those distributions as an average across many opponents, or how do you take into account how adaptable?
Yeah, so the style vector that we used was just getting a frequency count of those different shot types. So currently it's static, but you can imagine that these distributions will change. But that's where we add in the contextual feature. So that's another secondary feature which will change or just find the features which are important. So instead of modeling it, instead of changing the model in the model, we're actually just doing it by the features, and then the decision tree will find it out itself. Yeah.
Patrick, this is great work as always. One thing I've been interested in is, I guess, your player style vector. And you always hear stories about, basketball, everybody's watching Steph Curry's workout routine before the game. Ray Allen was famous for, taking tons of shots before the game. Have you done any analysis to look at whether you'd be better off trying to get incremental improvement on your strengths if you're an incredible sharpshooter and just being slightly better versus trying to fill in one of your weaknesses? You can sort of imagine that translating to the player style vector and how that would improve your win probabilities.
Yeah, so we haven't looked at that. So essentially what we're trying to do, and a big thing about our research, is just finding the right representation. So once we have the right representation, we can plug it into a model to optimize for the specific task. So just say you had a particular task, which you ask, we'd be able to personalize and actually do knowledge discovery and do better prediction for the things that you're looking at. But no, we haven't done that. But maybe we can chat afterwards. I'm sure you have a lot of good ideas in this space.
To what extent, if at all, would this be useful for in-game live tennis wagering?
Absolutely. So it's just information, right? So we have an information source that no one else is using. If it's predictive, given that we give it in real time, I'm sure we... so that's basically what we're trying to do, right? We're trying to do better prediction. And a good way to compare it is actually the market. So if the market's efficient, we're not going to do better. But if we have an information source which no one's utilising, if it's better, maybe the predictive market will use our information as well. Yeah. But that's basically it. So we want to do prediction. We want to do better prediction. If we can beat the market, that shows our model's doing pretty good. Yeah.
Do you foresee this being more of a storytelling tool, on broadcast and stuff like that, or more of an actual player training type tool?
Both. So it's a very good point. If we empower the domain expert, they can find the things that they want. So just say you're Carl and you're writing a story or you're a broadcaster on ESPN, you can find the patterns which can back up your story. If you're a player, you're playing an opponent. You can actually drill down and find the patterns that you want to find. So that's the thing. We want to just find patterns, okay? And different patterns are important to different people. So if we can empower them to find these patterns themselves, that's great. So my biggest pet peeve, I love statistics, but going through these spreadsheets, it's a nightmare, In terms of story, you need to tell a story. It's how we remember. It's how we act on it. So if we can allow people to find their own story, that scales, and that's really exciting in my opinion. Yeah.
Can you go into some more detail around how you calculate the point win probabilities through the course of the point and as they fluctuate?
Yeah, so essentially what we have is that we have an observation X, and so given the current shot and the previous shot, we just predict probability, so a continuous value between 0 and 1. So it's just a very, very simple classification problem. So the way, basically the secret sauce is how you actually train it. So in terms of our labels, so we have 0 for all the shots in the training set which were which the player lost, and there are 1 for all the shots that the player won. So essentially, at the classification stage, it basically weights each shot in terms of whether it's more likely to win or not. So it's just a frame-by-frame analysis, but our method's pretty smooth, and so we're getting these nice smooth predictions. So that's the important thing. So we haven't done much temporal smoothing. Well, we haven't done any temporal smoothing because the previous probability is going to be very, very strong in predicting what that next probability will be. So we've just done it snapshots.
Thanks, Patrick. So one of the things I've been interested in is how much history is important in predicting future shot outcomes. So I was wondering in particular, is there information that you find when you look beyond the previous shot, or are players just largely responding to the shot that they just received?
So that's a very good question. So something that we're working on, part of the data science group, is these temporal models. So recurrent neural nets, long short-term models are very effective. So not only, so you can do it in terms of a hidden Markov model. You could look at the previous state, or you could have longer chains looking 2 or 3. But what you're actually more interested in is previous points or previous interactions. So how can we model these long-term dependencies? And it may not be Markovian. There could be distinct patterns there. So I think it's an open research question. But if you look at the other domains, these temporal models like recurrent neural nets have been very, very powerful here. So that's something that we're going to apply. Yeah.
I'd like to thank Patrick again. I can give him another round of applause. And that's it for the presentations in this room, but there's going to be poster presentations over by the Weston Bridge with the 8 finalists, as well as another 16 posters. And please remember to vote on the app for your favorite research paper.